All right, we're going to try to finish up the course today because the last sections of Cal 1 deal with the integrals, the antiderivatives. We have definite integrals. We have indefinite integrals. And then we have areas between curves. All right. Definite integrals between functions. So we've talked about definite integrals. What is a definite integral? A definite integral is a number. What does that number represent? The area under a curve. Actually, it's more to it than that. Because if you think about it, if there's our function f of x, and if this is our area, a definite integral is the area under this curve, f of x, above the x-axis and between the lower and upper bounds. So it's a little bit more to it than say area under a curve. But it gives us a number. It gives us an area of value. That's what we did last section. This section, we're going to deal with, well, a definite integral looks like this. It's a continuous function from A to B. That's where we ended up last time. An indefinite integral. That's what we're dealing with today. And the definite integrals between functions. We're done with that one. We're going to do both of these today. So what do you think an indefinite integral is? If a definite integral is a number, it's a value, then an indefinite integral is a function. Because we don't, since it is indefinite, we can't come up with a value. Remember, when we have a definite integral, when we take the integral of it, what we end up with is the upper bound minus lower bound. That doesn't work that way with indefinite integrals. With indefinite integrals, what it's telling us is this. For an integral to exist, the function for this definite integral to exist, the function has to be continuous, and if it is continuous and has a derivative, then it also has an antiderivative. What does that mean? Which means this. Right. If this is my function, I take a derivative of it. This is the derivative. I thought you could just put f prime. Then the integral of a derivative is back to the function where it began. This is the part we're going to have trouble with for the most part, understanding that concept. So if we take the integral of a derivative, we end up with the function originally. So are there more functions than just one that can have the same derivative? Give me an example.
Well, like the constant can be different.
Constant's always going to be zero.
Like the original function
Yes.
can be this different, but it's not the same derivative.
Right.
Like 4x plus 6 and then same plus 8.
Very good. Very good. So the only different, so we can have multiple antiderivatives to the same derivative. I mean, the functions can come from. The only thing different is the constant. And that's what we're going to cover today. So the formula we'll be looking at for today is the integral of a function, f of x dx, is equal to its antiderivative plus some constant. And there could be multiple of those. How do we find those different ones? There's a whole bunch of process, because think about, if I give you a derivative, what could everything else that could be involved with it? So we have to think, we're going to develop methods of finding antiderivatives. So here we have the first one. We'll be using substitution. The substitutions of what? Remember when we did derivatives, we had derivative of e to the power u. If y equals e to the power u, what is its derivative? If the function is e to the power u, what's its derivative? EU du. Yeah, because take the derivative of e is just itself times the derivative of the exponent. Okay, so basically what this is looking at is using the chain rule in reverse. Because remember, once we take the integral, we end up with the original function before we take a derivative of it. So if we have a function u to the power n plus 1 divided by n plus 1, that's some function. And if we took a derivative of it with respect to x, what would that equal? If y equals u to the power n plus 1 over n plus 1, what would u prime give us? How do you take a derivative? What does the chain rule say? Okay, so what's the derivative? Remember, if our function was originally u to the power n plus 1 all over n plus 1. How do you take a derivative of that? Good question. Why would we not use the quotient rule? Is this a quotient? Looks can be deceiving. It looks like one because there's a fraction line, a rational equation of thing. But what's on the bottom? What does n represent? It's just some number. Whenever we talk about quotient rule, we have to have a function on top of a function. So it has to have a function with respect to x over a function. Is there an x? No, n is just a number. What this is saying is something like if y was u to the 5th over 5. No. Take a derivative of that. Because this is an exponent. What would the derivative be? What else? You're missing something.
It doesn't the last homework though.
And you're taking
already.
and u is a function with respect to x. Because every time we take a derivative, it's with respect to x. U is simply a substitution that we have in there. So the derivative of this function, as you said, the power, what happens to the power? It comes down. So we have n plus 1, subtract 1 over n plus 1. Just work it out. The n plus 1's cancel. N plus 1 minus 1, the 1's cancel. So we have u to the power n. Since it's a function with respect to x, du dx. There's the derivative of it. That's the chain rule. Now we got to work backwards. If I had this, remember, if I started with this, what does this number represent? That's my derivative. So if I go u to the power n du dx, and I'm integrating it, so it's with respect to x. So I took this equation, put it in there. What that's really telling us is this. So if you had an integral of u to the power n du dx, the x is canceled. So what this would give us is the integral of u to the power n du How do we take an integral of this? When we take integrals, we have to work backwards. Remember, this is the derivative. This is the derivative. Where did it come from? It came from this. How do we do that? Well, we have to take whatever this is. How do we get to 5? Add 1. What about the bottom? Well, whatever is here, I add 1. That's what this formula here tells us. So what this is going to give us is u n plus 1. Whatever I change the top, I have to put it on the bottom. Plus some constant. So the integral of this, u to the power n du dx, is equal to this. Why is that important? Now we have a formula that we can start taking the integrals of things. So here's our formula we'll be using for the rest of the day.
Or does it matter on, was that just strictly a textbook?
That's just textbook. It's just, I'm showing you a straight up shortcut here. But in essence, what they're doing is the dx's cancel, and the integral gets rid of the derivative. So let's look at let's look at an example here. Let's work backwards. Actually, before we do this one, let's do some practice ones. Because this one is taking a big jump already. We'll come back to this one. If you had that, what would the integral be? No.
X to the fifth.
No. You're falling in the trap that every student in calculus is always falling into. Look at the formula we just defined. What is missing in your answer and what we have?
Constant.
Remember when we first started this course, we said whenever you take the limits of things, you have to remember you have to put the limit of this, the same thing here. We're going to take integrals, indefinite integrals, and then we're going to forget to put the plus c at the end of it. If you forget to put the plus c, guess what? It's wrong. Because if you don't put a plus c in there, that means it's zero. There's nothing there. Even though c can be zero, or it could be 1, or it could be 2, which tells us that this equation has an infinite number of parallel type of integrals that I have to take. So do not forget to put the plus c's behind it. Find me the integral of that one.
Would this be simply that function squared over 2 plus
Good thought. I see what you're thinking. Yeah, because the power here is 1. But even if it was so, wouldn't that be the u? We would need to have du dx behind it. In order for this to work, we have to have the du. So if this is the u, where's the du? So good try. I see the thinking there, but no. Go back to the basics. Always start off these things. Look at, do we know any rules we can do with this? When we first started discussing integrals, well, this is a sum and difference rule. We can look at each one of these separately. Remember that rule? There's another rule. We had the constant multiple rule. The 3, it can go out in front. The 2, since it's a constant multiple, so I took all the constants, the coefficients out of there. So what's the derivative of x, or integral of x to the 5th? Very good. No. Yes, I see what you're doing. Yes, you could do plus these, but they're constants. At the end, we'd add up all the constants, so we'd have a bigger plus c at the end. So whenever you have to make this, just put 1 plus c at the end of it. But yes, but you're absolutely correct what you're doing. Then the next one is minus 2. Plus 5
Squared.
plus 2 Thanks for playing.
Yeah.
Because right now, what is it? There's nothing there. There's a 1 right there, right? But what is a 1? A 1 is x to the 0 power. So when we add 1 to it, we get that, plus c. So now we simplify everything. The 3 and the 6 cancel. The 2 and the 4 cancel. So we have x to the 6th over 2, x to the 4th over 2, plus 5x squared over 2, plus 2x plus c. Because you think about it, what's the derivative? What if the derivative gives you a 1, what would the function have to be? X. The derivative of x is 1. I know. It's just this kind of the basic stuff that because we're thinking of more difficult stuff. We want it to be more difficult. So the basic stuffs are going to be eating our lunch. So if you think about what is the derivative that gives us a 1? It's just an x. The derivative of a constant would be what? 0. So it can't be a 0. What's next above a 0 is an x by itself. Okay, we'll do one more. You don't need your cheat sheet. You can draw a picture.
You said bring.
I did. Yes, I did. Touche, you win.
I'm trying to save myself away.
Get it? What's the answer? What's that?
Plus.
Yes.
Okay.
Yes. Because if you use the unit circle, remember this is sine, cosine, negative cosine. So if what derivative gives us negative sign as a derivative. Remember I said that derivatives go to this way, antiderivatives go this way. So what's the integral of negative sign? Cosine plus c. Very good. No. So I was going to give you a more complex one, but not yet. So let's go back to this one we had here. Let's do this one. But I want to put the formula back up there. So our example was the integral of x cubed plus x to the fifth, 3x squared plus 1 dx. Remember, this is why we talked about the first method we're going to talk about is substitution. Because if we can take this long monstrosity and make it look like this, it's easy. So when we look at we have to find what is u. Well, u's the one that has the highest exponent, usually. So what's my exponent? 5. That's n. Here's u. U is what's inside here. This, yes.
Usually the thing with the high sex one, because when you get to the infinite scales, nothing else.
Yes. Well, for another reason. Because remember, when we use the chain rule, if we start off with a function like this, what would the chain rule tell us? First, take the derivative of the outside. So we have to 5, this x to the 4th. Times what? The derivative of the inside. So the derivative of the inside. Is this the derivative of this? Is that du? Yeah, so since it's with respect to x. So what we have here, this is our u to the 5th, and this is du dx. So those cancel. Not really, but we're making it look like this now. So we have integral of u to the 5th du. Isn't this one a lot easier to look at? So what's the integral of u to the 5th? Plus c. Now resubstitute. What is u? U is this equation there.
At the end of the problem, we have to.
Is that?
At the end of the problem, we have to plug the u back.
Yes, because we have to put it back in the way it was started off. So the first, yeah, that's the whole substitution is take this big monstrosity, put it down something that looks easier we can deal with, and then what at the end, put it all back together. How do you test it? Well, this is our answer. If it's truly our answer, if we take a derivative of this, we should end up with this. Do we? If this is our function and we take a derivative of it, do we end up with this? We'll call that our CYA. Check your answer. If y is equal,
CYA stand for? Right here. Oh, check my answer.
Yeah, in the business, you're right. So what is our derivative of that? Well, this is a chain rule. We have this inside equation and outside. So take the derivative of the outside. This one stays on the bottom. So we have 6 x cubed plus x, 6 minus 1 is 5, all over 6, times the derivative of the inside. The derivative of c goes to 0. So the 6 is canceled. X cubed plus x to the 5th times 3x squared plus 1. Is this what we started off with? Yes. So see, that's the connection we're trying to make.
How do we know that?
This function?
Yeah, because in the first step, we're like, is this our review? Was that given to us or did we just?
Well, no, because okay, once we finish this equation here, we said this is how we're going to check it. We have this equation here.
Okay, but I'm just saying, when we looked at that first example,
Oh,
the assumption already made that that was the derivative, is that the?
well, no. We can look at it. Take a derivative. If this is u, take a derivative of it. Is it du?
We're
That
testing to see it.
yes, because if it's not a derivative, then it can't fit in this formula.
Yeah, I just make sure.
Exactly. And that's the most important part. Because if this is not the derivative of this, then we have to do something else,
Okay,
which we're going to have an example like that in a little bit.
okay. We need to base next one first.
Well, yeah, we'll decide which one is u. We have to first define what is u. And the derivative of the inside cannot have an exponent. So that's why our first guess is look for the one with the highest exponent. And whatever's below that is our u. Example 2. Square root of 2x plus 1 dx. Here's a situation. What do you think our u is going to be? The u has to be on the internal. Because how would we rewrite this? We could rewrite this saying 2x plus 1 to the power 1/2 dx. The u part has to be the internal part. So now that we have that, we need to have a du. What's du going to be? If that's u, what's du? 2 dx. Because the reason it's dx because when you take the derivative of u, it's with respect to x. Move that over there. So du is 2 dx. So we have u to the power 1/2. Well, we have dx. We need to have a 2. Do we have a 2 dx anywhere? Because du is 2 dx. What's missing? We have a dx. Do we have a 2? Nope. But we can just put a 2 there. If you put a 2 inside there, we can counteract it by putting a 1/2 out in front. So if you ever have to input a number, a constant number inside the function, you have to put the opposite of it outside. Well, let's see what that looks like. So here we have u to the power 1/2. We need to have a 2 dx because this has to equal du. What is 2 over 2? I wrote too many things there. So we have 2x plus 1 to the power 1/2 dx. The internal function is u. The derivative of u is 2 dx. Here's the dx. We don't have a 2. What's the coefficient of dx? 1. So it's 2 over 2. Because we need to have a 2 in front of it. So that 2 can stay there. Where does this 2 come? It goes out in front. Now, I can change this to u to the power 1/2 du. U is that part, is under the exponent. Du is 2 dx. Take the integral of, so that stays out there. Take the integral of u to the power 1/2. It's the same way we've been doing it. What's the formula for it? U to the power 1/2 plus 1. Whatever's up there, since we're integrating, it goes on the bottom also. Plus c. So what is 1/2 plus 1? So here we have 1/2. That's the leading coefficient. That's this one. Yeah, I'll write this. So inside here, I have u to the power 1/2 plus 1 over 1/2 plus 1 plus c. One half plus 1. 1 is the same thing as 2 over 2 because the denominator is 2. So it's 1/2 u to the power 3 over 2 over 3 over 2. This is all algebra now. We're done with calculus. Whenever you hit fraction over fraction, what do you do with the denominator? If it's a fraction, flip it and put it in front. So the 2's cancel. So we have 1/3 u to the power 3/2 plus c. Are we done? What do we need to do? Yeah, remember, u was 2x plus 1. I think, yeah, 2x plus 1. So put this back in there. We get 1/3 2x plus 1 to the power 3/2 plus c. When I was in school, that would not be an acceptable answer. Why? Because the original question was given to us with radicals. if you're given the common convention of mathematics is if you're given radicals, your final answer, if it has to be in radicals. So 3/2 is the same thing as 1/1/2. So what that says, it's 1/3, 2x plus 1, 1 to the power 1/2. So it's 2x plus 1 to the 1, 2x plus 1 to the power 1/2, because this is the same thing as 1 plus 1/2. So it's 2x plus 1 over 3 times the square root of 2x plus 1 plus c. This is the way your answer should look like. But because the programmers are lazy on these LMSs is they take the shortcut and just leave the answer like this. Both ways will work. I'm happy if you get half that far.
But you don't give us credit for half of that far.
No, but I would just be happy. You could live the rest of your lives knowing that I'm happy with you. So far, so good?
Yeah.
Remember, the rule we have to live by is the integral of u to the power n du dx is the same thing as u to the power n du.
So I guess that question, because this is really the first time we are mathematics learning that we really deal with substitution. You don't really
In a
deal
full-fledged, right.
You don't really deal with it.
Well, in algebra, actually, when you deal with systems of equations, you deal with substitution there. You have to take one equation, solve for a variable, substitute in the other one, but not in this level. This one is full-fledged. It's necessary. It's the only way we can do it. Because it's part of our function.
That's where I'm-
Yes, but we do use substitution a lot in trigonometry. And those will be our bigger examples we have here. So this is the conversion from our integral. What we will normally see is this. And that's the answer. Theorem 6 is a substitution rule. Now let's put a name to it. If our substitution, if u equals g of x, if it's differentiable, remember, what does it mean to be differentiable? What are the conditions for it to be able to take a derivative of it? What else? Chapter 2 coming back to haunt us. Yeah, the limit has to exist. The function has to exist at that point, and they have to be equal to each other from both directions, right? So if u equals g of x, that's our substitution. It's a differentiable function. Whose range is an interval I, and the function f of x is continuous on that interval, then the integral of our function f of g of a composite function times the derivative of that function is equal to f of u du. Remember, it says if u equals g of x and g of x is differentiable, which means we take a derivative of it. Why did I take a derivative of it? Because what does the chain rule tell us? The chain rule epitomizes the composite function property. Remember what a composite function was? A function within a function. Whenever you have a function within a function, you have to use the chain rule. Take the derivative of the outside function times the derivative of the inside function. So what this is saying is, in place of g of x, if I put u, so if in place of g of x, if I put u, what is g prime? If it's u, then it's du dx. Then that dx, they cancel, so we're left with du, which is what that says. So this is the substitution rule. And we're going to be using this. Let's look at the next example. We'll be using that a lot more. Ready for trig? I'm glad you brought your paper. I'm not going to lie to you. This stuff may look understandable. Now, I'm never going to say easy with this stuff. But there are so many possibilities, so many ways you can go on these. If one way doesn't work, try something else. If that doesn't work, try something else. Find this integral. So whenever we're doing these integrals, what we want to look at first is determine what u is. What is our u? Yes. It's always the internal function. 5x plus 1. Once you find u, then what do you got to do? You also have to find du. So what's the derivative of 5x plus 1? Since this is a function with respect to x, well, it's actually du dx equals 5. But if I multiply dx to both sides, I get du is equal to 5 dx. The reason that's important because now we can rewrite our function five dx is what du is. This is u. This one looks like a lot easier to take the integral of. Look at our, so what function gives us secant squared as our derivative? So it's tan u plus c. And now we resubstitute. U is 5x plus 1. So the answer is tangent of 5x plus 1 plus c. Do not forget that plus c. So I guarantee you, you're going to be doing your homework, you're going to enter it, and it's going to say wrong. Only because you forgot a plus c. Cosine of 7 theta plus 3 d theta is a
Below last one, or, the last one, so we went from secant squared to, or, we went secant squared u du, and then it just went to tan u.
Mhm.
I guess I'm missing where we, the du went, right, because we got rid of the integral, and we got rid of du.
Yeah, because the integral of secant squared of u, this integral, the derivative of tangent is secant squared. The derivative of u is du. So that's the chain rule aspect of it. So this is the result of the chain rule of this function. Yeah, it's going to be hard. It's going to be hard looking backwards now. Where did this come from? So just as you said, what happened at du? Well, that's the derivative of the inside. This is the outer function. This is the inner function. How about this one? What's my u? So what's du? Seven what? D theta. We were taking with the theta. That's another thing. You have to make sure you use the same symbols they use. So with this, for our du, do we have 7 d theta? What's missing? We're missing a 7. So if we put a 7 there, that means we have to put the reciprocal of it out here. So we have here is 1/7 cosine u du, because this is du, this is u. Now we don't have to worry about any of the special stuff. The integral of cosine is what? Sine u. So now what do we got to do? Plug it in. What is u? Everybody get that? The answer should be no. The answer should be plus c. Because if you got what I had, you didn't finish. You said no. What'd you get wrong?
Like the plus C, I'm not gonna have a hard time with that.
Oh, no, get in line. Every professor, everybody who's taken calculus before you, same thing. Because it's not natural just to put a plus c after anything.
I'm also having a hard time with, you said it's getting rid of the U. It's already. There's a lot of like internal stuff you have to memorize to get rid of. Usually
You have to remember, this is the derivative. This is the derivative. So if you took the derivative of sine u, how would you, if it was y equals sine 2x. What would the derivative be?
Two.
Cosine 2x times 2. Because it's the derivative of the outside, which is cosine. Leave the 2x alone. Then the derivative of the inside, which is what this is telling us. So this is the derivative of the outside. Leave the u alone, times the derivative of u. And yes, that's what's going to be the hardest part, is you have to think about where did it come from.
Once we drop it, integers, we drop it.
Yes. Yes, pretty much that's what's looking at. Because once you find you drop the integral, if it's an indefinite integral, the integral replaces by plus c. Example 5. Which one is this? Oh, this is here. Here we have this example. Take the integral of that function. Again, first thing you have to determine what are u and du. So what do you think our u is? Yeah, has to be the x cubed. It can't be the x squared, because how can this thing go to an exponent up here? This can be e to the, so this one could be e to the power u. What's du going to be? Yes, because whenever you take a derivative of u, it's a function of x. So you have to put the x behind it. Or kind of like an implicit differentiation. So do we have a 3x squared dx in our original equation? What do we do have? We have an x squared. That's this part. We have a dx. That's this part. We're missing a. So we just put a 3 there, and we divide by 3 in front. So now I have 3x squared dx. So that's du. So what's the integral of EU? The integral of EU is simply EU. Think about it. As you just said earlier, if this is my function, what's the derivative of EU? EU times the derivative of U. So if y is equal to EU, the derivative is EU times du. That's what that is. Yes.
This example, please, whenever we're getting our meters, always make sure that anything that's missing is added to.
To a point. If it's a number, yes, we can put all the numbers we want to because we can counteract them in the front. But if it's an X that's missing, we can't just throw an X in there. That would, yeah. So if it's a number, a fraction, or decimal, we can do that. But anything else, we have to think of another method.
I just lost my 31 down there.
This one? The first half it didn't have a 3.
We added,
Yes. Well, oh, and this stuff. So what do we need? We need to have 3x squared dx.
in the,
3x squared dx. So all these three together become du. Commutativity, right. Yeah, and that's why earlier it was all nicely put together. But very simple. Okay. There better not be a fire drill. Not on dead week. Example 6. X square root of 2x plus 1 dx. So first thing you have to do is determine u and du.
You would be. So that's what one, change that one.
So what would du be? 2 dx. Okay, so what are we missing so far? So we put a 2 in front of there and a 1/2 out in front. All right, so that means we have 1/2 out in front. The integral square root of u, this is du. See a problem here? There's an x there that's got to be allocated, that's got to be taken care of. How do we do that? In other words, what we're doing here, we're taking all the x's and putting them in terms of u. Can we change x to in terms of u? Let's use that.
That doesn't give me confidence.
Well, because this is where x and u are related. U is equal to 2x plus 1. So what does x equal? If u equals 2x plus 1, because of equality purposes, u minus 1 equals 2x divided by 2, x has to equal u minus 1 over 2. So in place of x, I put a u minus 1 over 2. You see, everybody follow what I just did there? Because now only have functions with respect to x.
So.
Because everybody, not just.
Well, so
Like, this is not intuitive, this is very hard. It's not hard, it's necessary, it's just not intuitive, that's not the route that my brain.
no, I agree with you. And as I'm saying, it's not easy. But when you think about it, what the concept is, we have to define what is x. We have to put x in terms of u. Because everything else Everything else works in terms of u. So here's the relationship. If 2x plus 1 is equal to u, if 2x plus 1 is equal to u, what does x equal? That's what we need to know. Because the only place we can define what x is in terms of u is from this relationship. So take u equals 2x plus 1 and solve for x. Yes, it's yeah, within one within the other, right? Well, that's more transformation because I'm reconverting it. It's not really a substitution. It's kind of a substitution because I'm transforming this equation to x, and then I'm substituting back in there. Not yet. This is as hard as it gets because then from here it gets easier. It's the algebra part. Well, this is a fraction. We have a 1/2 out in front already. This equation is 1/2 u minus 1 square root of u du. So this constant multiple can go back out in front. So 1/2 times 1/2 u minus 1 square root of u du. Let that sink in real quick. Because first off, the problem we had is what happens to x? Has to be in terms of u. Because that's what we're taking this integral with respect to. So we have to find u with respect to x. We did that. We plugged it in there. Since there's a fraction in there, we think we can take out the 2, and now this is what we have. 1/2 times 1/2 is 1/4. Square root of x is the same thing as x to the 1/2 power. So u minus 1 to u to the 1/2 power du. Distribute. Which gives us 1/4 integral of u minus 1 u to the 1/2 power du. So I distribute. I get 1/4 u times u to the power 1/2. 1 times is u to the power 1/2. What do you do with the exponents? Add them. So it's 1/4 u to the 3/2 minus u to the 1/2 du. Integral of u to the 3/2 du minus the integral of u to the 1/2 du. This is a subtraction rule, the difference rule. What's the integral of u to the power 3/2? Plus 1. 3/2 plus 1 minus u to the power 1/2 plus 1, 1/2 plus 1 plus c. Yeah, so it's This is 2/2. This is 2/2. 2/2. So it's 5/2 over 5/2. 3/2 over 3/2. Since these are denominators of a complex fraction, a compound fraction, we flip them. So we have 1/4, 2/5 to the 5/2 minus 2/3 to the power 3/2. The 4 and the 2 cancel. Oops, I have to distribute first. So this one has this 1/4 I distribute to both parts. And this 2 and that 4 cancel. So I have u to the power 5/2 over 10 minus u to the 3/2. 2 times 3 is over 6. And what? And our u value is what? There's our answer. Don't believe me? Take a derivative of it. I'll take your word for it. I agree with you. There are a lot of moving parts there. And just think about where it all started from. It all started from this small equation here. All because of this little x right there. If it doesn't wash out with when you do a substitution, if it's still dangling out there, you have to take. This is the only place where you can tell me how x and u are related.
It doesn't matter if there was a 3x.
It wouldn't matter if it was a 3x, right?
It would still be the same.
With a 3 coefficient.
Is there a reason why we changed the radical? Well, we went from
Here?
Yeah.
Yeah,
We left the radical.
because we couldn't distribute if we didn't.
This could be had it as u to the 1/2 the entire time.
You could, oh yeah. You could have changed it here if you wanted to. It's just that I didn't want to, so I could get myself confused. Yeah, but you can do it anytime you want to.
So are only distributed one, yeah, the very top part. How do we get end up with u1 times u1? Break that.
Where this one came from?
Break that.
Ah, okay, yeah. That starts from over here. X itself was u minus 1/2. So x is u minus 1/2. Since that's a multiple, I took 1/2 out and I took it back out even further. So this is u minus 1/2. Since it's a constant multiple, I took it out in front, so it's 1/2 times 1/2 is 1/4.
But I come go from the top step to the second step. How do we do that one? So u to the 1 times u to the 1. How do we break down the steps to get to?
Well, what if it's the same as this? If I had that distributivity, what would happen? It's plus, right, same thing. It said this is my coefficient, I multiply it to each one. So it's u times u to the 1/2. U to the power 1. Yeah, it's the small things that will confuse you. And once you think about it, so I knew that. It's just that there's so many other things going on here that you're just stuck doing that. And that's why it's gonna in your homework, it's gonna take you some time. This is just try and try and try. But you have to be very, very, very patient, very slow.
2 hours.
Yes.
Yes, I'm not, and that's the reason on my homework assignments, I don't have more than no more than 10.
There was one homework assignment that took like 4 hours with 3 to-dos. It was hard.
Which one was that?
I can't
They have multiple
remember.
parts to it?
Yes.
And see, and that's what burns me up is when I look through them, it doesn't tell me 1 out of 8 parts. It just says, here's the question. Well, that's pretty easy. I can do that, no problem. But then they ask you so many sub questions. And that I can't see from where I am. So I do apologize on that. So but pretty much, I mean, even after all said and done, is everybody can you at least follow along the logic there? Yeah, and it's the algebra. Because calculus is right there. That's it. That's okay. Is a substitution. Once we did that, the rest is algebra.
And it's because the X, we didn't have an X, so we have.
You have to find it with respect to you. Yes, because there's that one. Okay. Now, that's whenever you have an extra dangling X, a variable out there that you have to define. Because when you use substitution, all X's have to become U's. All X's, you cannot have an X and a U. You can't take an integral of that. So that's the hard part. This looks pretty benign, but it's not. Because can you use a chain rule in this? Not really, because would you take it? What's the internal function? Is it sine x? Is it sine squared x? Is it x? Inside, outside. There's too many pieces in here. So you can't take the integrals of squared functions or cube functions. What you have to do is figure out how to convert those to terms where it's like double angles or triple angles. So in your sheets, what does sine squared x equal?
One half. One minus. 2x.
So 1/2
Minus 1 minus 2. Minus 2.
Yeah, so 1 minus cosine, the double angle, over 2. Right. Because now we can use the chain rule here. So it's the integral of 1 minus cosine 2x over 2 dx. The 1/2 goes out in front. So I have 1 minus cosine 2x dx. So it's 1/2 integral of 1 dx minus the integral of cosine 2x dx. What's the integral of 1 dx? That's an easy one. How about this one? What's the integral of cosine 2x? Because this is a chain rule, we have to define what is u. Then what's du? What's missing here? So I put a 1/2 out in front. So this is 1/2 cosine u du. So this is du. And this is u. What's the integral of cosine u? Sine u. All that plus c. All right. So now we can distribute, get rid of the parentheses. So we have x over 2. 1/2 times 1/2 is 1/4. Sine u plus c. So x over 2 minus u is 2x. There's your answer. What do y'all think?
I'm lost.
We're at. You okay? Here we convert it. We can't take a sign because this can't be u because we can't take a chain rule here, a chain rule of a chain rule. So we have to convert it to a double angle.
Lost. We got, the x from one dx to the x. I guess
This one here.
yes, I guess I,
All I did was distribute. I did the difference quotient, a difference rule. So it's the 1/2 stays out front. Now I took the integral of 1 dx minus the integral of cosine 2x dx.
like I said, I thought that x would have had to be converted into.
Well, we haven't gotten that far yet. Here's at this point, once I had separated them, I defined 2x is what u is, and then du is 2 dx. I don't have a 2 here, so I needed to put one there. Everything's got to be done in its own time. So once we did that, I have 1 minus, from this point here, I had 1 minus integral of 1 dx minus the integral of cosine 2x dx. Now I convert it with respect to u. And that's what I'm doing here. I went from here to here.
We don't need to convert the one dx into
This one?
respect to.
No, because its integral of 1 is just x. This one needed to be because it's the chain rule. This one's just a regular rule. That's the thing about it, is when we do the difference or product rule, sum or difference rules, each one of these are their own functions separately.
Makes sense.
Yeah, because you're thinking, well, it's one equation. No, because of this minus sign between there, because of that minus sign, it splits them up to two separate functions. Treat them both independent from each other.
I think I was thinking too. Why is the, why do you have one dx? Do we have to take the derivative of the anti-derivative of one? Okay.
Yeah, because the function was 1 minus cosine 2x. So when I distribute it, I gotta take derivative integral of both of those. And it also helps. What function gives us a derivative of 1? X. Okay, then B was the integral of cosine squared x dx. So we figure out what is cosine squared x. Since sine is 1 minus cosine, this one's going to be 1 plus cosine. So we have 1 plus cosine 2x over 2 dx. The denominator is a constant multiple, so we'll just factor it out. So 1 plus cosine 2x dx. Distribute the integral inside both of those, so it's integral of 1 dx plus the integral of cosine 2x dx. Now is where I can define u and du. So here's a dx. Doesn't have a 2, so I put a 2 in front of it and a 1/2 out in front. Oops. Yeah, I figured that. So it's 1/2. The integral of this first part is simply x. So this is cosine u du. Substituting both of those in there. Distribute. We get 1/4. The integral of cosine u is sine u plus c. So it's x over 2 plus sine u over 4 plus c. And u is 2x. What do y'all think?
Participation. We suck at participation. I'm not gonna root for the plus C. And I'm gonna get all the homework assignments wrong. I'm gonna be very salty about it. Reach mine. Then they give you a new problem.
Well, just add the C.
Or whenever you do integrals, make sure you put a sticker somewhere that says plus c. I know, everybody's gone through it. It's just that some people break before others. Some people will catch on because they hate to have to redo it. So at least you guys get to redo it. Back in the old days, we'd get our papers back F.
No.
Red mark,
then
red
you at
mark.
least get credit. At least you get credit for the paper.
But-
The new learning system does not give you credit. I don't like that. I don't feel like writing that in your evaluation because that is a school problem. But it is really hard to.
Oh, don't worry about the evaluations. I'll fill them out for you.
Great, too.
Yeah, it's true.
You my example, it's
Does, but it's still like. It's.
I almost feel like that you might example makes that harder. Sometimes.
So it reminds me of like what I need to do. Sometimes I just forget what I need to, like, how to start. And then I would, in my example, I'm like, oh yeah, and then look at my.
Yes.
Turns
But
into like a 15 paragraph thing, you know.
no, yeah, it does.
Which takes forever.
Yeah, that,
You need to think before you write.
So what's the integral of tangent? Or we could look at it this way. Tangent is what? What's u going to be? In this case, we have two functions. Is it going to be the top one or the bottom one? That's tangent. No. It's if it's top and bottom, 99.9% of the time it's on the bottom because the derivative of sine is not cosine, is cosine, but when we do this, the integral of it is not going to help us any because I'll show you why. If u is cosine x, what is du? Do we have a negative sign dx? No, we have put negative and put a negative out in front. So now what we have is we have this top part is du and the bottom part is u. Do we have an integral of du over u? It's the integral of ln. Remember the derivative of ln? It was du over u. Look at your sheets. The derivative of ln is du over u. So the integral of du over u is ln u. Because your ln functions, you cannot take the ln function of a negative number. And since cosine, these functions can be positive or negative, we have to make sure that stays in the absolute values. So ln of u was cosine. Are we done? No. Remember the rules of logarithms. Whenever you have a coefficient out in front, what does that mean? The property of logarithmic functions is you cannot have exponents. When you have an exponent, that comes out in front. So working backwards, if we have something out in front, so what that tells us, we have ln of 1 over absolute value of cosine x. What is 1 over cosine? There's your answer. This goes back to algebra. You cannot have, in other words, you couldn't put the answer as negative ln absolute value of cosine. Because by the properties of logarithms, you cannot have a coefficient. If you have a coefficient, it becomes an exponent. If it becomes an exponent, it changes the position of your ln, or your cosine, made it a fraction. I know all these rules from algebra and trig and and you thought it was gonna be easy.
Maybe it was gonna be easier once we got through up here. So that's why.
Yeah, I concur that that did not ring true. That is not a theorem or a law. I disagree.
Isn't it mostly mechanical what we're doing?
But it's not intuitive.
There's a difference between easy and intuitive, because the easy part is easy. You think about it. Is it mechanically difficult? No. The part that's makes it difficult is the user themselves. It's a user issue.
I don't think so. I think it's a software issue.
Or it can be both. How about this one? dx. Ex plus e to the negative x. What this one says is, speaking of algebra and trigonometry, sometimes you may have to do some algebraic manipulations before you do anything. Because think about everything that it may be algebraic, maybe trigonometric. What can we do to make this thing look easier for us? Well, actually, we have two of these. What can we do with both of these functions algebraically that would make life much easier for us? Well, we couldn't, because if we did that, we couldn't do it on the bottom just yet. What this one gives us a trouble is what this one looks like is e to the x plus 1 over e to the x. So what we have to do first with this equation is multiply it by 1. If we multiply top and bottom by e to the x, because that'll get rid of our fraction on the bottom. So we have a fraction of a fraction. So we have e to the x. On the bottom, we distribute. So e to the x times e to the x is what? Whenever you have the same bases, you add the exponents. E to the x divided by e to the x is 1. So now, can we define u and find du? What is my u? But this one can also be that. Because the property is whenever you have power to a power, you multiply. So if we made it e to the x, what's the derivative of e to the x? Dx. So on top, we have e to the x dx. On the bottom, we have ex squared plus 1. So, and we said u is that one, so it's du over u squared plus 1. So what function has a derivative of 1 over 1 plus x squared, or u squared? Or 1 over x squared? Look at your sheets. Look at the inverse functions. Because the derivative is 1 over 1 plus x squared. Would you get?
Cotangent?
Nope. Tangent. Because the derivative of inverse tangent u is du u squared plus 1, or 1 plus u squared, which is inverse tangent of e to the power x plus c. Okay. Now, is that intuitive? Not really. But what gave us a good hint was this negative exponent down here. It made it a rational function. You couldn't just multiply the bottom by e to the x over e to the x to get rid of the fraction. So I had to do the whole equation. So you see, the algebraic manipulation is multiplying by 1. This equation is going to be a little bit more difficult. What do we multiply to that one? So what do we multiply to this one to make it more algebraically easy to manipulate?
Right.
Now, can you guess why I did that? Let's think about it. This is the one where we multiply to that. So we get secant x times secant x plus tangent x over secant x plus tangent x dx. Because now, when I multiply this out, get the integral of secant squared x plus secant x tangent x all over secant x plus tangent x dx. So what's our u? From the last couple of examples, where was our u usually located? On the bottom. So so if that's our u, what's our du? What's the derivative of secant? And the derivative of tangent x is secant squared plus secant tangent. So if we set this as u, the derivative of secant is secant tangent. Derivative of tangent is secant squared, which is what that is. So the top part is the derivative. So that's du, and the bottom part is the u. So whenever you have secant, remember what the secant and tangent rules are, the derivatives are, because you have to expand them really big to get that. That's why we did the secant plus tangent, because we had to get secant squared in there somewhere. So the integral of du over u is ln u, and u was secant x plus tangent x plus c. Because that's what we did up here. That's the conversion. Let's see. How many more examples we got? A couple of more examples. The integral of tangent x dx is equal to the ln of secant x plus c. The integral of cotangent x dx is the ln of sine x plus c. The integral of secant x dx is the ln of secant x plus tangent x plus c, and the integral of cosecant x dx is the ln of cosecant x plus cotangent x. The ln of cosecant x plus cotangent x plus c. It'll make life much easier for you with just referencing. You have these on your cheat sheets, but you notice how the secant, how we got those? We did that right there. The beautiful thing is this. Once it's been proven, once it's been defined, you don't have to go through the work, do the work anymore. So if you have an integral of secant, don't bother working it out. Just use this formula sheet. Plug them in there. One more example. So as I said, I'm not gonna lie to you, it's not easy. There's a lot of moving parts. If one method doesn't work, guess what? Try another one. If that one doesn't work, try another one. And go back to the first one, because maybe you did something wrong. So
The curiosity, the test for this chapter is gonna be like 3 questions, because they're gonna take us forever, right?
I think for this chapter, I think it's 5 or 6 or 7 questions only. Even though there were like 7 or 8 sections. So you actually only had 5 sections, 6 sections. There's one more section after this. But that was a lot. I've been saying this how long? But this is tough because this is now showing us all the mechanical tools that we have to find integrals that aren't that easy. These are all indefinite integrals. Definite integrals can use the same stuff. But from there, we have to go f of b minus f of a, get a value. And these are just all examples of indefinite integrals. All right. So what's our u going to be? You okay? We can, but now think about that. If you did that, what would du be? Because we want it to be 2x dx. So our du, our u, will simply be the inside. Because when we take the derivative of that, we'll get 2x dx. So we have du over cube root of u. Yeah, the first guess would have been the whole denominator. But if you did that, then to take the derivative of it, we'd have a bigger equation because we have to use chain rule. So just let's use the insides of it. This one? So what would be our, oh yeah, the power would be dx to u to the 1/3 power. Because the rule is this. Whatever the root, this is your root. Whatever the root is, always the denominator. And whatever your exponent is the exponent in there.
They're used. It's inside.
Yeah, use whatever is inside there. So it's u to, so now we can rewrite that as being u to the power negative 1/3 du, not dx, du. So the integral of u to the power negative 1/3 is negative 1/3 plus 1, negative 1/3 plus 1 plus c. So negative 1/3 plus 3/3, negative 1/3 plus 3/3. So it's 2/3, 2/3 plus c. The bottom flips. And u again was x squared plus 1 to the power 2/3. You got a little bit easier? Easier. It's just that, yeah, again, another hard part is making sure you pick the right u. Because when you pick u, take the derivative, and you have to make sure that that is somewhere up here. Think about it. If our u was x squared plus 1 to the power 1/3, what would du be? Bring the power outside, subtract 1, times the derivative of the inside. You see how big it got really quick? So that's why this whole denominator could not be the u. So it's the only inside. So look, you have 2x, x squared. Obviously, it's telling us that this has to be the u. This is the du. It's subtle hints like that that we have to be able to pick up on. You know, some hits. But we just, again, it just takes practice. And the next section, the last section of our course is we're done with all this other stuff. Now we're going to look at, we have two functions, f of x and g of x. We want to know what is the area between the two functions. So how would we find that? Since it's area, we got to take the higher function, because if f of x is greater than g of x, then it's the higher minus the smaller. We have to take that difference. Basically, what's happening here is this. When we find this one finds the area under f. That's what this first one finds. Now we subtract the area under the g. What we're left with is what we're looking for. And then also, we're going to look at functions. Well, we're going to take it with respect to dy. Up until now, we've always taken it with respect to x. Vertically. Now we're going to look at horizontally. It's the same concept. Same, if it's horizontal or vertical, it doesn't matter. It's whatever, and this one, whatever is higher goes first. This one, whatever is farther to the right goes first. So this is the bigger one minus this one. It's this area minus this area. Gives us this area. That's what we're going to do on Wednesday. And that'll finish up the course for us.